So, hi everyone. Today we're here with Ellen. Ellen is a colleague from Germany, from our German team, and she contributed to this blog post, which is about how to build a cost-optimized chatbot with semantic caching. So, hi, Ellen. Can you tell us a bit about yourself?
Yeah, sure. So, first, thanks of all for having me here. My name is Ellen. I'm a specialist solutions architect at Databricks in Germany. So I specialize on topics around machine learning, data science, and AI. Also I have the honor of presenting the solution today on this call, but also a huge shout out to Ryuta and Neme, who were two of the main drivers behind the idea and execution of this solution.
Awesome, awesome. And so, can you tell us first, like, what inspired the, development of semantic caching, for chatbots?
Yeah. So one of the main ideas behind the semantic caching is to reduce the costs and the computational load. So what we have with RAG systems is that the queries are always sent to the large language model to get an answer back. However, in many cases, we have quite similar questions, but with some semantic variations. So some use cases we had in mind, for example, are chatbots for FAQs, for terms and conditions, or for internal knowledge bases. So something where you can imagine that there are similar questions coming in, but with slight semantic variations. And in those cases, maybe we do not need to ping the LLM, but we can actually send the query to the cache instead and get an answer that has been answered in the past for a similar question. So that's the main idea behind it. So to save time and cost and have better scalability, but also in a way you can actually have some response moderation because you know which answers have been sent in the past.
Awesome, awesome. So basically, the blog highlights inefficiencies in typical chatbot query handling, and this, like doing semantic caching, allows you to address those inefficiencies. So that's what motivated you to do that. Awesome. So can you tell us what is the significance of embedding-based vector similarity in the context of semantic caching?
Yeah, sure. As mentioned, we sometimes have questions that are very similar in meaning, but they are formulated in a different way. So what we used in our solution to build the cache is the Databricks Vector Search, which leverages the Euclidean distance. So what we do is, like with general vector database, we calculate the embeddings of the questions and we compare the similarity. So if we have an incoming query that is above a certain threshold to a question that has been asked in the past, we can route it to the cache instead of sending it to the LLM.
Okay, so you measure the similarity to determine whether or not you can query the cache instead of the LLM.
Yeah, correct. So in this case, our Databricks Vector Search does that for us. But we also go into that in our exploratory data analysis. But we also have some way of setting this threshold. So how can we determine when two questions are similar enough? Because that's like one of the big knobs in this solution. Like when do you actually have two questions that are similar enough that you can get the question from the cache, and when should you generate a new answer instead?
Got it. So that's something that you explain in the blog?
Yeah, in the blog and also in the first part of the code of the solution accelerator.
Awesome. Can you just, if we take a step back, can you walk us through the flow of processing the query in the system from input to cache and hit miss determination, like step by step?
Yeah. Maybe for that, let me quickly share my screen. So in the blog article and also in the GitHub repository, we have an accompanying image which describes the process flow quite well. So let me just zoom in a little bit. Exactly. So here you can see that let me do it like this. So here you can see we have the user query coming in, and it first hits the cache, so our vector database. And there we determine, okay, is there a similar question already to this one?
Yeah.
Yes or no? Then based on that, we have a router. So if there has been a similar question with an answer already in the past, we can retrieve this answer from the cache and just send that response to the user. If not, if it's below the threshold, then we have missed the cache and we go into a regular retrieval augmented generation chain. So we use some context and basically an LLM to get a new answer and send that response to the user. If that happens, we also append this question and this answer to the cache so that it can be used in the future if similar questions will come in the future.
So then, Ellen, do we have two caches here? Then it's like actually two vector stores, one for the cache, the semantic search, and then one for the actual RAG.
Yeah, correct. We have the vector store for the RAG, which is like a regular RAG chain. So here we have our we can also go into it in the demo, but in our demo case, we are working with some questions about Databricks documentation. So in the RAG case, we have the vector search with Databricks documentation where we can retrieve documents that may answer the question. And in the semantic cache, we have these question-answer pairs that have been answered in the past.
Awesome. And how does semantic caching help reduce the operational cost of running a chatbot on LLMs like ChatGPT, for example?
Yeah, so this is again where probably it will depend on your data at the end of the day, because if you have a lot of similar questions, you will be hitting the cache quite often probably, and you can reduce a lot of cost because basically every time you hit the cache, you are not querying the LLM. But we also have implemented some metrics that can actually help you track this. So we have the hit ratio, how many queries have been sent to the cache and how many queries have not been sent to the cache. But yeah, generally speaking, every query that will go to the cache will reduce the operational cost.
Oh, that's awesome, because then it can help you also define the threshold and also see if like it's a, like if it's an appropriate solution for the data that you have.
Yeah, definitely. And we also, in the EDA, we also provide like some help and some guidance how you can get started in determining that threshold.
Awesome. And the blog touches a bit on embedding drift. What are the strategies that you recommend to mitigate the impact of this drift on semantic caching?
Yeah, correct. So, as mentioned in the process flow, if we have a query that was not in the cache before, and we get the answer from the LLM, we will append it to our cache, right? Which means that our cache will grow over time. But maybe also depending on the data, we might have, like, for example, certain new types of questions that start appearing, or maybe also some questions that were in the cache in the beginning but are not as relevant anymore. So that is why the solution also implements some ways for so-called cache eviction. So there are different strategies to do that, and we also go into that in the code. But basically, that will ensure that you can clean up your cache to ensure that you have room or space for the most relevant or the newest or the most often asked questions.
Amazing. Should we look at the demo?
Yeah, sure. So let me share my screen. So with the solution, we have two things. So first of all, we have this blog article. And there in the blog article, we also have linked our GitHub repository. So here we are looking at the GitHub repository. So it's in Databricks Industry Solutions. And you can get started using it by just cloning this into your workspace. So I have already done that. And then you will have everything from that repository in your workspace. So here we have all the notebooks, so you can go through them step by step. There are some helper functions, for example, for the cache. Maybe one thing you want to change or take a look at before you get started is the config. That basically determines which vector index you are using, how you want to name your model endpoints, which catalog and which schema you are using. But after you have done that and adapted the config, you can get started with the first notebook, so this introduction one. Let me make this a little bit smaller. Yeah, and then you can go through these notebooks step by step. So let me quickly go through each of them and basically, just summarize what is happening there and what are the most important points there. So in the introduction notebook, as mentioned, we are using some synthetic data in our case. So we are using some Databricks documentation. So let me quickly go there. And in our case, we have 10 questions as a baseline. So these are 10 questions and answers which we have generated, which are possible questions about the Databricks documentation. Then on these 10 questions, we have bootstrapped them to create some slight variations for each of the 10 questions. So basically, they are asking the same thing, but they are formulated slightly differently. And by doing this, by this synthetic generation, we can know what the base question was. So basically, which question it should be similar to. Now, this is something, if you want to start trying the solution accelerator, you can start looking at this data. But then if you also have maybe your own labeled data, you can also try it with that and actually go through this introduction and EDA to see if maybe you need a different threshold, because we have done that based on our data. So maybe let's take a quick look at what the data looks like. So here you can see these are our synthetic questions. So these are our 100 synthetic questions. And you can see each of them has a base. So basically everything in base 1 is related to a similar topic. And next we want to see what the distances are between them. So here we also use the Euclidean distance, like in our vector search product. And what we do next is that we generate all the possible pairs between all the questions. So we have 100 times 100 questions. So 10,000 possible pairs. And we know which of these pairs are similar or not. And because
one question. So on the Euclidean distance, is this something we have to tune, or it's the only way to calculate similarity at this point?
No, you can also use a different distance metric. In this case, we wanted to stick with what is also used in the vector search, just to make sure that way you are also calculating it in the same way that it is done in the product.
So if people are using a different vector index, does that mean that they would have to change how they, like the distance, right? How they calculate the distance?
Depending on which distance metrics that vector index offers. But this is also one that is used quite commonly. So I would expect that, that it's also possible with others. And then because we have these similar and dissimilar pairs, we can actually compare the distributions of the distances. So what we see here in the blue is that we have the dissimilar pairs. So for example, we have a question from base 1 with base 3, and the orange ones are the one that should be similar. So for example, we have 2 questions that are based on base 1. And what we can see here is that indeed the similar questions, they will have a higher threshold. So this line is not linearly separable in our case. So for example, what we could do here is that we can see here, okay, we have the non-similar pairs that are completely separated here. So in our case, we set the threshold at 0.01. In that case, it means we miss some of the similar pairs, so some of the orange ones, which could have been sent to the cache, but are not. So we have a precision recall decision in this case. But in this case, we decide it's better to send some similar questions to the cache because we do not want to have questions that are actually not similar being sent to the cache. So this is where you might need to tune a little bit, and if you want to adapt it to your own data, check these distributions.
And I guess you decide based on the use case, like, do you care about latency more or do you care about the accuracy of the application, right? And you tweak accordingly.
Yeah, for sure. And I think it will also depend a lot on the distribution of your actual data, because here we have like this synthetic data, which is very evenly distributed with the 10 classes, but maybe you also have like a classic long tail distributions. So you maybe have like a lot of questions around a similar topic and then some questions which are about very different topics. Yeah. Exactly. And then in the next part, the data preparation, this is the part where we prepare the vector search for the RAG chain. So if we quickly go back to the image, this is the part where we are preparing this retrieval part. So this is very similar, I think, to similar demos. So we don't need to go into the details of it, but at the end we will have a vector index, which we can query, which has our Databricks documentation. So for example, if we ask something like, what is model serving, we will get some similar documents from the documentation. Then in the next part, we are actually creating two RAG chains. So one is like the RAG chain that's also common in a lot of demos. So this is a normal RAG chain that uses the retrieval, augment, and generation part. And we use this because we actually want to compare this to our RAG chain with the cache. So here, again, I think there are no big surprises, so we don't need to go through the details of this one. But here we define our chain, we log it with MLflow so that we can track it, and we deploy it using model serving. So at the end, what we will have after these two notebooks is two endpoints. So this is our standard RAG chain. And then we will also have the RAG chain with the cache. So maybe let's just go to the RAG chatbot with the cache right now and go through the steps that happen there and why it's different to the normal RAG chain. So first of all, we need to initialize some steps. And next we immediately start with our cache object. So we have here everything that is related to our cache so that we can instantiate the cache, but also do anything we want to do with the cache.
So I have a question. Then the cache, is it a different implementation of the vector sets? Does it need some specific aspects into it?
In our case, we are using a direct vector search index. And we are initializing an empty vector search index for that with direct access so that we can load directly the question answer pairs into that. But other than that, it's like the regular Databricks vector search index. Yeah, we can also quickly go into it. So what we have in here are, sorry, wrong one. I wanted to go into the cache. So what we have in here are some methods basically for creating the cache, which uses the vector search endpoint name where we want to create it on. Then we create a direct index and we can load the data. So warm the cache basically with our existing questions and answers. And we also go through this step by step in here. But basically everything related to the cache is in there. So the first thing we do is to check if we already have a cache and if we need to empty it. This is something we do in this case, for the demo, just to make sure that we are starting with an empty cache so that we can check some things there. Then we create the empty cache, so there is no data in there yet, but this is then the direct vector search index. And then in the next step, we load into it our synthetic data. So this was the base data, so the question and answer pairs. Exactly, and we can actually also quickly take a look at what this looks like. So let me quickly go there. Or maybe actually we can check it here. So here you can see we have our cache vector search index. So in our case, we have these questions, their vector embeddings, and then the IDs. And here in this case, you can see there are already more questions in there because I have already used the system, so questions were already inserted. But in the beginning, we will have these 10 questions here, which were created by the system.
Got it.
Yeah. And then in the next step, it's also quite similar to the RAG chain from other demos. One of the differences is, though, that we have some logic when we need to hit the cache or not. So for that, maybe let's start at the end when we are actually calling the chain so that we can go in there and break it down. So what you see here is the chain that we are calling. So we are getting the user query. And then the first thing we do is we go to the semantic cache. This is one of the methods from that cache object. And then we see if we can get the question from the cache, yes or no. Then in the next step, we have our router, and that will based on if we have a question or not. So here the router, if there is no question returned from the cache, it will run our RAG chain. And if there is a question returned, it will actually just return that question from the cache. Then if we run the RAG chain, there is also one major change, I would say, compared to the regular RAG, because we need to upsert our answer. So this is also one change we have made. So here we are not just calling the model. So here we get the response from the model, but we are also storing the response from the model in the cache.
And then another question. So how, when you update the cache or upsert into the cache, so how do you decide if you have already a similar question in the cache, or you just update? Do you see my point? Yeah.
Right now, this is fully based on the get from cache, so on this threshold. So if something is not in the cache, it will be upserted. This is, of course, something where you could potentially also think of adding some logic if you really want to upsert all the questions in the cache. But right now, we upsert everything that has not been gotten from the cache.
Just to clarify.
Okay, so when we say...
Go ahead.
Oh, sorry. When we say upsert, do we mean append, or do we mean we have a logic to understand what we have in the cache and we add if necessary? Or we don't add if not necessary?
No, we in this case, we append, exactly.
We append, okay.
Yeah, we can also take a look there. Yeah, so here we basically add them to our cache object. So.
Okay.
Yeah, I was also just wanting to clarify what we mean with this upsert step. So basically, this happens if there's no question in the cache, in which case you want to take this question and put it in the cache so that if in the future, if a similar question is raised, we can retrieve it. And so with Maria, we clarified that it's an append. Got it.
Yeah, correct. And right now, here really, as soon as the RAG chain is hit, everything goes into the cache. But we do also have some strategies for cache eviction. Yeah. We can go into that in a bit, where you can also see, for example, maybe which questions are used frequently or
Got
not. Yeah, but at this point, they come from the cache or they go into the cache. Yeah. And in the next steps, also very similar to regular RAG chain, just that we also need to add some additional files and log them as well with MLflow. So we also need to add our cache, of course. But other than that, we log the model and we also deploy this one. So now we have 2 serving endpoints at the end. So we have our standard RAG endpoint and our RAG chatbot with cache endpoint, and we can query both of them. And as mentioned, in this case, we have these 2 because we want to compare them in the next step, so in the evaluation.
Yeah, for anyone who's not familiar with all the latest MLflow capabilities for LLMs, you should really check it out, because it really allows you to evaluate your chain and really, trace, for each step, like have some observability and know what went wrong. So because people may be familiar with ML flow for traditional ML, but there's a lot of really cool features for LLM workloads as well now.
Yeah, correct. It's a good point. We actually also show some of that here. Like basically after we have defined our chatbot, we also test it with a few examples. So here you can see we ask a question and we know it has not been asked before. And we can also see from the MLflow trace that the router decides, okay, this is not in the cache, but we need to run the RAG chain. And then if we ask a similar question, but slightly different after that, we can also see from the trace that in this case, it actually gets it from the cache. So this is also very helpful in tracking this back. And we also use this later on to actually get this hit ratio.
Awesome.
And Ellen, both irrelevant, sorry to this, it just came to my mind. So both vector stores are wrapped in the same model and served in the same model serving endpoint, right? Like the caching and the RAG are wrapped in one MLflow model.
Yeah, cool. So you mean like in this case, in this case it's all in one MLflow model with the cache and the RAG chain. Yeah.
So when you showed the serving endpoint, like one endpoint represents the basic RAG endpoint, and the other endpoint was representing the RAG plus cache.
Yeah, correct. Okay. Yeah. So this is the one with the standard RAG, and this is the one with the RAG chatbot with cache. So we can also take a look at that one. Yeah, so if we go to the experiment of that one. Let me quickly go here. You will also be able to see it in the artifacts then of that one, that it is. So this is also what we log in the chain directory. But basically here we have our chain cache. But we also have some other code related to the cache around that. And everything we log there is also here under chain. And here you can also compare how the two of them are defined. So the chain and the chain cache. Yeah. Then in the next part, we evaluate both of the chains. So we have our standard RAG and we have our RAG chatbot with cache. And we wanted to compare, so first of all, actually the time and how often it hits the cache, for example. So some more performance-related metrics. But we also wanted to take a look at some evaluation quality metrics because our expectation was that for some of them, maybe with the cache, we will see a slight drop, which we could indeed confirm. It was a slight drop in relevancy, but correctness was actually quite similar. So let's take a look at those results. This is, of course, something that is to be expected because you might have some performance increase, but for that, a slight quality decrease. And this is, of course, also something that you should consider for your application, like what to optimize for. But in this case, for the evaluation, basically we call both of the endpoints. So the standard RAG endpoint and the RAG endpoint with cache. And for both of them, we ask for the response for our 100 synthetic questions. Then in the next part, because we have these 10 questions with the base and with the answers, we can see what would have been a good answer for this. So then we do some pre-processing to get these evaluation sets in our case. So here you can see the RAG chain that was always run. So we have our question, we have our predictions from the model, and we have these base answers that we compare it to. And for the cache part, you can see that we have our questions, we have our predictions. So here we can see in some cases the predictions are actually identical to the answer, so it has been hitting the cache. But in some cases, also a new answer has been generated, and then we compare also these two. Then we use MLflow LLM as a judge, and we want to get some metrics related to similarity, correctness, and relevance. And we run that on both of them, and then we compare it. So what we can see here are our standard results and our cache results. And what we can see, so for example, the answer similarity is a little bit different, and also the answer correctness and the answer relevance. So we can see here that the answer relevance is actually slightly higher for our standard RAG results, which is to be expected because every result is generated from scratch, right? So hopefully it should be better. And for our answer correctness, we have
4.8
here also a slight decrease, but pretty minor. So it's mainly the relevance in this case. So this is something to keep in mind.
Amazing.
And Ellen, one question as well. So in terms of cost, I can see how hitting the cache can be cheaper, I guess, right? Because you don't execute a lot, you just grab it, return it.
Yeah.
But is it actually? Given that you have to support 2 vector endpoints and one model serving endpoint. I guess one model serving endpoint you'll have in any case. It's just now you're supporting just 2 indexes in the same vector endpoint.
Mm-hmm.
Is this what you do, right? 2 indexes in the same vector endpoint?
Correct. It's 2 indexes on the same vector endpoint. I would say probably this also depends a lot on the size of both the vector search indexes. So I would say in our case, we start with a pretty small cache. But of course, what we also have seen already in the one I just showed, that it keeps growing with every question that was not in there, which is also why the cache eviction is important. But in general, and this will also depend, of course, on several factors. For example, also which LLM are you using for your RAG chain? For example, if you are using a large LLM, then the cost increase, of course, will be larger. Yeah.
Makes sense,
Yeah, but we also, so we do have some metrics to track that as well. So here we go into some more performance-related metrics. This, of course, will also depend on which endpoint you are using, how many queries you are sending. But what we can see for sure is that the RAG chain with cache was a lot faster than our standard RAG chain.
Oh, that's good. Really good.
Yeah,
like across 10 questions.
100 questions, that was. Yeah, exactly. Yeah, and we can also see in our case, so the cache was hit around 70 times. So only 30 questions should have been inserted to the cache. This is then also something you can track. But also we can see that the cache was hit quite frequently. And we can also see that if a query comes from the cache, it is actually a lot faster. So these are also some interesting metrics you can take a look at. Yeah, and then finally, maybe a few words about the cache eviction. So we have provided 2 strategies for that. And also in this notebook, we provide some suggestions on how you could improve that as well. For example, if cache eviction is a relevant topic for you. But what we have here is, first of all, the first in, first out strategy. So basically the oldest items from the cache would be removed first. And this is especially useful if you know that maybe you have data that changes frequently over time. So maybe questions that were asked a few months ago might not be asked today, something like this. And the other strategy which you can use is the least recently used strategy. So here you go more by popularity of the questions, right? So this is useful if you know that certain questions might be asked very frequently, like in customer support, FAQs, for example. And there, if you see that a question is maybe asked only a few times, it could be removed from the cache. And in this here we also provide some explanations around the limitations and how you could also improve this for your use case if you want to.
Are both implemented, or you have to code the logic?
Yeah, both of them, you can go into the cache.
Oh, very nice.
Yeah, and here you have the FIFO or the least recently used.
Excellent,
Why
nice.
do we need to clean the cache? What's the downside of like putting everything in the cache and just not worrying about cache eviction?
Yeah, so one issue is that it will grow over time, especially if you are handling lots of questions. So you will just have a huge vector search index. So that is then also, a question of cost and time. And the other thing is, of course, also relevancy, especially, for example, with this least recently used. Maybe you don't need certain questions to be there, but this is also something, that also depends on your data and your data understanding. Yeah.
Makes sense.